Asha, we had talked about electrophilic substitution, and we had kind of talked about most of the reactions of electrophilic substitutions related to benzene. Now, the thing that we had to talk about was that I told you that there are lots of benzene derivative compounds. This is what we were talking about, and you got arenes. So it's a benzene with a carbon chain. You got phenols. You got phenylamines with benzene with an NH2. You've got chlorobenzenes. You've got benzoic acid. You've got benzaldehyde. You've got nitrobenzenes. And I told you that all of these, they undergo electrophilic substitution because they do have a benzene ring, except that there would be slight differences. And we talked about the kind of groups that are attached to benzene. You've got a 2,4,6 directing group, usually referred to as just 2 and 4 directing groups. So if the benzene is attached to any of these groups, an amine, an OH, or just an O with a carbon chain, or an amide, or an alkyl chain, or a chlorine. The other ones are 3 directing groups, which is that they're attached to NO2 or NH3 or CN or aldehyde or carboxylic acid. So you have these 2 types of groups. Now, the thing is, what effects do these groups have on the benzene electron cloud? We're going to discuss that. So I'm going to take a benzene electron cloud, which we have over here somewhere. We had drawn benzene electron cloud. 1 second. So let's take this one. So I'm going to copy this. And we are going to work on this. Okay, so if it's just a benzene molecule, then everything, all the electron cloud, everything is distributed evenly. Okay, so if it's just an electron cloud, the electron cloud is evenly distributed. And it's a symmetrical molecule, everything is identical. And the electrophile would get attached to any of the carbon atoms. It doesn't really matter. It's exactly the same. So I'm going to pick the first few. I mean, these ones. I'm going to pick these ones. That what happens if you've got an amine, or you got an OH, TK, or a carbon chain or a Cl, TK, all of them. So we're going to study these. So let's start with OH. What happens if, what goes wrong when you have an OH? The thing that happens is that if instead of an H, I've got an OH. Okay, so instead of an H, I've got an O that's bonded to an H. The thing with the OH group is that this OH group has lone pairs. I mean, it's got lone pairs, and these lone pairs, what happens to them is that they tend to overlap with the benzene electron cloud, because remember, oxygen is a very small atom, so the electrons want to be distributed. They start overlapping with the benzene electron cloud. So this is what happens. So the p orbitals in oxygen, the lone pairs in oxygen, which are full of electrons, they start to overlap, and they start overlapping with the benzene electron cloud. As a result, the electron density over here, on this side, the electron density kind of increases, because oxygen's electrons also start overlapping with benzene's electron. So the negative charge over here kind of increases. Is that point clear? Ruba, is this clear? Lubena? Ethan?
Yes, sir.
Yes.
And all the other electrons, what happens to the other electrons is, because one side is now more negatively charged, so all the other electrons, they kind of they kind of get repelled. They get repelled to the other end. Because there's more negative charge on this side, so all the other electrons, they kind of get pushed to the other side, which is why the negative charge on this carbon atom also increases. So the thing that happens is that once you have an OH group is an electron donating group. So that's known as an electron. That's known as an electron donating group. So it pushes electron density on the benzene electron cloud. The negative charge over here increases, and all the rest of the electrons, they get pushed away to the other side, and the negative charge on this side increases as well. So the end result is that you've got more negative charge on positions. What positions? So I'm going to start numbering them. So this is your position number 2. This would be our position number 4. This one is position number 2. And this over here is going to be our position number 6. I mean, this is 1, the OH group that's attached on carbon number 1. So on carbon number 2, the electron density is high. On carbon number 3, the electron density is not that high. On carbon number 4, the electron density is high. At carbon number 5, the electron density is not very high. At carbon number 6, the electron density is higher as well. So the electron density, kind of the electron cloud, which was previously evenly distributed, is now no longer evenly distributed because the electron density is higher on this side and higher on that side as well. But not very high on the carbons that are on position number 3 and 5. So this is what's going on. Just one second. So this is what's going on, and this is what is meant by 2-4 directing groups. You don't use the word 6 because 2 and 6 are kind of the same position. You just flip it around. 2 and 6 are kind of the same position. So the electron density is higher at position number 2, 4, and 2, 4, and 6. That's just this. So it's higher at position number 2, 4, and 6. So if you have an electrophile that's roaming around like the NO2 plus 1, which was our electrophile, or I mean, the electrophile is more likely to be attracted to, it's more likely to be attracted to these positions. 2, 4, and 6. So it's going to be more attracted to these positions. So just one second. So anyways, our electrophile is going to be attracted to position number 2. It's also going to be attracted to position number 4. So is this point clear? That the electrophile now has a liking for certain carbon atoms and a disliking for other carbon atoms. Is this clear?
Yes, sir.
So just going to write that electrophile is more attracted so it's more attracted to positions 2, 4, and 6. Or you can just call it 2 and 4. And that kind of happens with all electron donating groups. For example, whether it's NH2, OH, or CH3, etc. Now the thing is that when you talk about electron donating groups, and let me just simplify this, let me just add the benzene, just a second. So here's my benzene. I'm going to simplify everything now, and I'm going to draw a couple of them. So there's one, here's another one, here's another one, here's another one. So electron donating groups, right? OH, we just did that. So that's the lone pairs on O mixing up with benzene electron cloud, and there's more electron in C on this side, and all the other electrons get pushed to the other side. You've got NH2, that's also, it also has a lone pair. The N has a lone pair. So the lone pair on N overlaps with benzene's electron cloud, and the electron density becomes greater at position number 2, at 4, and at 6. I said then you've got arenes, which are carbon chains, CH2, CH3. And arenes, the same thing, the electron density increases. And all the other electrons, they get pushed to the other side. And finally, you've got chlorine as well. Chlorine's got lone pairs, 3 of them actually, which also overlap with benzene's electron cloud, and the electron density increases at position number 2, 4, and 6. Now remember, it's the electron density is increasing, and any electrophile that's introduced would be attracted to these positions 2, 4, and 6. Now the only problem over here is that that the effect is not the same. I mean, all of them have electron donating effects, all of them. But the OH and the NH2, they've got a much larger electron donating effect. And even NH2 has a pretty large electron donating effect. Which is why what happens is that when it comes to phenols and phenylamine, the effect is really pronounced. Like the alkyl chains, they have an electron donating effect, but that's very slight. I mean, this thing would happen, but it would be very slight. And similarly with Cl. Cl has an electron donating effect, but it also at the same time, I mean, the lone pairs would overlap with benzene's electron cloud, but at the same time, it also has an electron withdrawing effect because the Cl atom is kind of electronegative. So the overall push of the electrons on the benzene ring, that's not that large. So the point is that the first 2 cases, the electron donating effect is pretty large, which is why the negative charge that builds up over here is pretty strong. And the electrons that accumulate over here, so the overall effect is pretty strong. This is known as an activated benzene ring. In all cases, electron density on benzene increases. Pi electron cloud, it increases. In all 4 cases. And if the pi electron cloud density increases, there's going to be more attraction for electrophiles. And if there's going to be more electrophiles, so this one is known as, I mean, these types of benzenes are known as activated benzenes because their reactions are going to be more vigorous because of the stronger attraction for these electrophiles. So they're known as activated benzene. Why? Because faster electrophilic substitution reaction would happen. So anyway, so those who have joined late, at last time we were discussing these groups. We were discussing 4 directing groups and 3 directing groups. So I explained this, that when you have a benzene, normally benzene electron cloud is evenly distributed. It's the electrons are everywhere, evenly distributed. But once you add an OH group to it, then one side is, I mean, the molecule is no longer symmetric. The OH group has got lone pairs, and the lone pairs, they start overlapping with benzene's electron cloud. So the electron density on this side increases. You got more electrons coming in, so there are more electrons on this side. All the other electrons, they get repelled, they get pushed away, and they accumulate on the other side. So now the benzene electron cloud is no longer evenly distributed. You've got more electrons on this side because of the electrons coming from this side. So at position number 2 and 6, and there would be more electrons on position number 4 as well. The positions were given based on this one. The OH was considered to be attached to carbon number 1. So this is 2, this is 3, this is 4, 5, and 6. So at positions 3 and 5, the electron density is not going to be very high. Y and 4, is this clear? Okay, if one side has a higher electron density, I mean this side, because electrons from the OH, the lone pairs, they start overlapping with them. So you got a high electron density. All the other electrons, they get pushed away, they get repelled. Okay, because of the higher negative charge on this side, these electrons over here, they get repelled and they accumulate on position number 4. Amna, is this clear? Yes or no? Is this clear to everyone? Adam, is this clear to Bena?
Yes, sir.
So this is what is meant by the 2,4 directing groups. And all these groups, the 2,4 directing, whether it's NH2OH, alkyl chain, Cl, or amides, they kind of have similar effects. The electrons are always being pushed onto the benzene ring. The electron density is always higher. So the benzene ring is no longer symmetrical. It's the electron cloud is no longer evenly distributed. You got more electrons on one side now. And then we said that not all these groups produce the same effect, or they produce the same strength of effect. For example, the OH and the NH2, they've got a larger electron donating effect because they've got lone pairs. I mean, the CH2, CH3 doesn't have lone pairs. So the push that they have, I mean, if the electron donating effect that they have is very, very slight. And for Cl, I told you that it does have lone pairs, and it does donate some electrons onto the benzene ring, but the Cl atom is also very highly electronegative, so it also has an electron withdrawing effect. So the net effect, the net push of electrons that would overlap onto the benzene pi electron cloud would be very slight. So electron density on benzene pi electron cloud increases, there's more, and which would result in more attraction for electrophiles. I mean, electrophiles are going to be very strongly attracted because the benzene now has a lot more electrons. The negative charge is a lot stronger. So any electrophile, whether it's bromination or alkylation or acylation or nitration, it's going to be faster. This is known as an activated benzene. There's going to be faster electrophilic substitution reaction because the electrophile would be very strongly attracted to it. Like if you do bromination, and bromine is positive and this bromine is slight negative, the electrons over here will attract the positive bromine very, very strongly. And the electrons in the double bond, they're going to be repelled very, very strongly. So the electron cloud over here would have greater polarizing power. Okay, is this point clear? So Aruba, is this clear? Suhail, Ethan?
Yes, sir.
Yes, sir.
So we're going to study electrophilic substitution again. I'm not going to talk about the mechanism. I'm just going to state that when we were doing electrophilic substitution, we did this. That a normal benzene was not able to polarize the bromine molecule. So you needed a catalyst from the other end. The benzene was trying to push the electron away. The catalyst on the other end was trying to attract the electron to itself. So the polarization was weak. So you needed a catalyst. But when the benzene electron cloud is activated, like in this case, or most cases, so if the benzene electron cloud is activated, just, I mean, like in the OH case, and when the electron donating effect is very large, then a lot of times you wouldn't need a catalyst. It's going to be a faster reaction. So one by one, we're going to discuss electrophilic substitution again, and we're going to see what happens to the conditions of electrophilic substitution. So let's talk about arenes first. Substitution of arenes. Now, what happens in arenes is, okay, what happens in arenes is that, I mean, they have the same conditions as benzene. Because alkyl chains have very slight electron donating effect. So they've got very slight electron donating effect. So for example, let me take that. So it's going to be kind of the same reaction, like you do bromination. You react this with bromine. And there's a carbon chain attached. So the reaction would be faster compared to normal arenes, or just very slightly faster. Compared to benzene. You can remember a benzene with a carbon chain, that's an arene. So this reaction would just be very slightly faster compared to a benzene. The conditions are going to be the same. So you've got the same exact conditions. And what you're going to get is, remember, it's a 2,4,6 directing group. So I'm going to copy the whole thing. And I'm going to get two different molecules as a product. So remember, because of this carbon chain, which was having an electron donating effect, the electron density was higher at these positions. So which is why the bromine is either going to be attached to this carbon, or it's going to be attached to this carbon atom. So it's either going to be at this second position, or it's going to be at the fourth position. So you're going to get two products, both are equally likely. 3,5 is going to be less likely. 3,5 positions, they would have lesser electron density, so the bromine will not be attracted to it. And the other molecule that's going to be produced is going to be an HBr molecule in both cases. So is this clear?
So what about the position 6?
It's the same position. Like if I draw this, take position number 6. So if I draw position number 6, 1 second. So the position is going to be kind of the same position as position number 2. Like if the bromine bonds at position number 6. So remember, the first one and the second one are kind of the same thing. You just pick it up and put it upside down. It's going to look like this. Is this clear?
Yes, sir.
So the thing is, you just call it 2 and 4 positions. Okay? Usually the 6th position, there is no 6th position. It could be that you could get a bromine here and you could get a bromine over here. If there's a bromine at both positions, then one of them would be 2 and the other one would be called 6. In that case, you're going to call it 2 and 6. So is this clear? Electrophilic substitution of arenes, that it's kind of the same as benzene, almost no difference. Even the conditions are the same. We didn't talk about the conditions. The conditions are going to be an FeBr3 catalyst or an AlBr3 catalyst would be needed. So you would need a catalyst. Not that different. I mean, out of the two Zoa, it's going to be the, I mean, they have equal probability. The one that's not going to be formed is the one that's going to be at position number 3 or position number 5. That would be highly unlikely. I mean, it could form. I mean, that's a possibility, but that one would be highly unlikely. Is this clear?
Yes, sir.
Yes, sir.
As a next part, then we can talk about electrophilic substitution we can talk about electrophilic substitution of what? Of phenols and phenylamine. And the same with nitration. Let me just quickly do nitration. You're going to have we didn't talk about nitration, so I'm just going to copy everything. Nitration would be kind of the same. Okay, so let's just so nitration is going to have the same conditions: concentrated nitric acid plus concentrated sulfuric acid. So let's rub this off. So concentrated nitric acid and sulfuric acid. Plus the temperature would be the same as well, 55 degrees centigrade. Instead of the Br, you're going to get an NO2 and an NO2 at position number 4 as well. So it's going to be NO2. And there's going to be NO2 at position number 2 and at position number 4. And you can get rid of this. Okay, so that is nitration. Same thing, exact same thing as except for the whole position thing. Okay, everything is the same. Is this clear?
Yes.
The thing is electrophilic substitution of phenols and phenylamine. Now with phenols and phenylamine, what you have is you've got a pretty accurate benzene ring. So now the phenol, it's highly activated. So they're going to be highly activated. What that means is you've got an OH, and we did discuss that the lone pairs are going to mix and overlap, and the electron density is going to be really high. Now, in this case, when it comes to a phenol or a phenylamine, or the other one, which is a phenylamine with NH2. With NH2. So it's highly activated. The reactions are going to be a lot faster. Okay, so it's going to be a vigorous, faster electrophilic substitution. So for one thing, you don't need a catalyst. Like if you're doing a reaction of a phenol with and you're trying to brominate it, you're doing a bromination reaction. And I can just, one second. So you have this phenol and you're trying to, here's your OH group. And you're trying to do bromination of this reaction. So the only thing that's needed is you don't need a catalyst anymore. The only thing that's needed now is Br2 aqueous. That's it. No catalyst is needed. And the reason is you don't need to actually, you don't need help polarizing it. Like if the bromine molecule approaches, because of the really high negative charge over here, the electrons are going to get repelled. This bromine would have a very strong partial negative charge. This bromine will have a very strong partial positive charge, and it's going to be attracted to the benzene even more strongly at this position or this position or this position. So the polarization is no longer an issue. You don't need a catalyst. Like in the previous case, you needed a catalyst, and now you don't need a catalyst. Okay, is this point clear? No catalyst is required. Okay, just like alkenes. Is this clear?
Yes, sir.
Okay, just like alkenes would react with Br2 aqueous. A phenol would also react with Br2 aqueous. And not only would it react with Br2 aqueous, the phenol benzene electron cloud is so activated, it has such a high electron density that the bromine usually gets attached to all three positions. The second one, the fourth one, and the sixth one. Instead of being at one position, the electron density is really high. So the positive bromine is going to be attracted to all the three positions. And so you get this thing. This one is 246 tribromo. Phenol, which is a white precipitate. It's a white precipitate, and this one is known as a test for phenols. Okay, so this is known as a test for phenols. Okay, so this one is used as a test for phenol, and you have to remember that if you add bromine aqueous to a phenol, it would produce a white precipitate, and the bromine would also get decolorized in the process. So remember this. So remember this particular test. Is this clear?
Yes, sir.
Yes.
Okay, and the amine would also have kind of the same reaction. It's kind of the same reaction for amine as well, so we can fit that in as well somewhere. Maybe the next page. So I'll just add amines. So amines kind of have the same reaction. So let's add amines. It's activated as well. And I mean, this one is obviously not used as a test for. No catalyst is needed again. And this time it's a phenylamine. And this one is 246 tribromo phenylamine. So tribromophenyl amine, which is, I mean, unlike that, it's not a white precipitate, but we can just find out. This one is not used as a test. So just 1 second, 2,4. Bromo. Phenyl. Amine. So let's see if there's a color property, non-flammable. We can just Google it. The image. Tribromo. Aniline, that is just found. So I just find this out. This knowledge is not required actually. But I think it's also white in color. Tribromoaniline. So maybe it's even the Wikipedia page is kind of small. Probably not a very important chemical. Let's leave this. Let's leave this at the moment. Forget the color of this. Just remember the other one for phenols. The test for phenols is that you get tribromophenol, and that's a white precipitate. Is this clear?
Yes.
Yes.
So let's continue tomorrow. Just make sure we're still doing electrophilic substitution, except for benzene derivative compounds. So okay, everyone, take care. Office.
Okay, sir. Tomorrow we will do 3-5, right? Compounds.
Which one?
The 3-5 groups.
Tomorrow we'll we're done with 246. I mean, these are the two ones we talk about a bit about Cl. That's also that we'll talk about this electrophilic substitution of Cl, and then we'll do 3-5. Okay.
Okay, sir. Allah Hafiz.
Okay, Allah Hafiz.
Thank you.